everyone. Welcome back. Our first speaker this afternoon is Mr. Emre Köroğlu. Mr. Köroğlu is the Deputy General Manager at MERİH. Prior to this position, he was the R&D Coordinator and Production Manager. He is a mechanical engineer with almost 10 years of experience in the product design and production side of the elevator industry. Today, he will discuss minimizing the mechanical losses on sliding door systems. Please welcome Mr. Köroğlu.
Okay, good afternoon, ladies and gentlemen. My name is Emre Köroğlu. I have been working in MERİH as Deputy General Manager. Today I will talk about the mechanical losses on sliding door systems, and I will try to show you some experimental data regarding some prototype applications. And let's first start with basic definitions. For example, what is the door, or what's our expectations from the doors, or what did we do on design to fulfill our expectations? From the engineering perspective, we can define the door as an electromechanical device. Especially the electromechanical part of the door is the operator, because it includes the motor, the driver, and other mechanical parts. So, we can directly focus on the operator to define our engineering expectations. Here, as you see on the screen, simple mechanics, easy installation and maintenance, small sizes, lightweight, operation reliability, high performance, less energy consumption and efficiency. All these will be considered as the engineering expectations from a door operator. So regarding these expectations, I think many studies are done, many chains occurred till now. So, what are these expectations? Sorry, what are these chains? Or in other words, what was done till today? In more recent times, we can say that a door operator with complex mechanics and simple electronics evolved to a door operator with simple mechanics but complex electronics. I mean, the mechanical structure of the door operator, slider crank mechanism, changed from the slider crank mechanism to simple bell pry mechanism. Similarly, low-efficient motors gave their places to high-efficient motors, I mean keyless motors, I mean direct drive. I will not mention the details, but maybe we can assume all of these are the headings. So, this evolution shows that great developments have been achieved, but it doesn't mean that development stopped. Never stopped. Because although our expectations will not change at all, always somebody will try to do something different. And today, I mean nowadays, it is the fact that most of the studies, research and studies on the door operators, focused on the power technology side of the operator. It's normal, because the rapidly developing technologies are leading the change. I mean information technologies, I mean the power technologies. These are the rapidly developing technologies and they are leading the change. It's the nature of development. But beside these studies on the power technology side, I think that it is necessary to do something more on the mechanical side. So that's why today I will talk about the mechanical losses. We have specified 3 points causing mechanical losses. And we have analyzed them under 3 topics as the effect of the mechanism, the effect of the guide shoes inside the seal, and the landing door effect. And now we ask these 2 questions. What are the components being used in general applications? And is it possible to minimize the losses by replacing them with their alternatives? Here is the answer of the first question. The components used in general applications. They are polymer rollers for the guidance of panel hanger inside the mechanism, frictional guide shoes inside the seal, and the spring for landing door. And here is our idea. We suggest to replace the polymer rollers with linear bearings. And we suggest to use rotational guide shoes instead of the frictional ones, and the counterweight instead of a spring. So our study is trying to find out what will happen after these replacements. To analyze the difference between these components, we have performed totally 8 different tests. The first 6 tests is just to compare the component with its alternative. But the last 2 tests is quite different from the others. Because in the last 2 tests, we performed the test with all components together. Before the test setups and their results, I just want to inform you about our measuring equipment. As you see in the picture, we have a MERİH door driver. We use this driver to measure the motor values, like voltage, like current, like speed. And then, to read these values from the driver, we use a special software, MERİH software. Then, we use another software called ScienceLab, it's like MATLAB or Mathematica. We use it to make the data meaningful. I mean, we use it to draw the graphics. And I have to notice that all the tests are performed through the opening direction, and we collected the data in every 5 milliseconds. And now, let's start with the tests. Here, our first 2 tests. You can see the illustration of the test setup on the black side of the screen. We have 2 different mechanisms, one with polymer rollers and another with linear bearings. We just used only the mechanisms, without panels, without seals, without spring or anything. Just only the mechanisms. Then we get the results, as you see on the graphics. We have 2 graphics for each test. One graphic for the speed and another graphic for the power. And then we compare these 2 graphics. As it is seen from the screen, the speed profiles seem similar. But the power graphics are quite different. When comparing these results, especially comparing the power results, we use another mathematical method. We try to simulate the average power values with locally fitted polynomials by an algorithm in ScienceLab. So we get the results like that. Here, you see the average power value in the peak speed zone. I mean, oops, it's quite difficult to use this device, yes. I mean this zone. The average power values are 8.9 watts for the mechanism with rollers, and it is 5.5 watts for the mechanism with linear bearings. So we find out the difference is 38%. Actually, it is quite more than we expected, but it is a fact. Then we continue with the guide-through effect. Again, you can see the test setup illustration on the next side. We have used same mechanism, same panels for the test setup. Mechanism with rollers. We used same motor, same driver. Of course, we operate both of them in with the same operational parameters. In the first test, we performed the test with the frictional guide shoe. Then we performed the test again with the rotational guide shoes. And we got the results as the graphics. Again, the speed profiles seem similar. But also, there is no significant difference between the power graphics. To see the results better, let's have a look at the simulated graphics. As you see, again we calculate the average of the power values in the peak speed zone, and we find out that 14.2 watts for the frictional guide shoes and 13.6 watts for the rotational guide shoes. So the difference is just only 4%. And actually, it is less than we expected. Maybe our rotational guide shoe design is not good enough. I don't know. Our R&D department is still working on it. Maybe in the future, if we repeat the test again with new designs, rotational guide shoes, maybe we will get better results. But for now, the difference is just only 4%, and it is what we have for now. Okay, let's continue with the spring effect. We used a mechanism with linear bearings. We used same panels, same motor and driver again. First, we performed the test with spring, and then we performed the test with a counterweight. And we got the results as in the graphics. Speed profiles are similar again, but the power graphics are significantly different. The spring effect is obvious in the peak speed zone. Remember, we were performing the test through the opening direction. So, at the beginning of the peak speed zone, the average power value is 17.7 watts. And at the end of the peak speed zone, it is 25.9 watts. To make a comparison, we calculate the midpoint of these two values, so we find out that 21.8 watts. The average of the power values for the weight, it is 16.5 watts. So the difference is 24%. Okay, up to now, we have performed totally 6 different tests to see the difference between the components. And I think it is time to summarize the results. First, we compared the rollers and linear bearings. Then we find out 28%. Then the difference between the frictional guide shoes and rotational guide shoes, the difference is 4%. And the difference between the spring and weight is 24%. We should read these results just the difference between the compared components. These results don't represent the overall power reduction on the door system. But we tried to find out the overall power reduction of the door system. We want to see it. So we performed 2 more tests, but now with real doors. not test setups. We have two different doors with same specifications, 4 panel central opening doors. The first door, we used polymer rollers, spring and frictional guide shoe together. And the other door, we used linear bearings, counterweight and rotational guide shoes together. Then performed the test with the same operational parameters, and we got the result as in the graphics. Okay, the speed profile for the alternative method is quite better than the other. But the great difference is on the power graphics. To see the difference better, again, let's have a look at the soluted graphics. You see on the real bar, the average power value just beginning of the peak speed zone is 43.7 watts, and it is 53.6 watts at the end. So the midpoint of these two values are 48.6 watts. The average of the power values for the alternative methods, it is 22.4 watts. So the overall difference between the general application and alternative methods is 54%. So, as a conclusion, we replace rollers with linear bearings. We use rotational guide shoes instead of the frictional ones. And we change the spring with a counterweight. Then we get 54% reduction on consumption.